Thank you. Just a little bit, since this is a celebration of Caesar's 100th birthday, I just want everybody to know I first met Caesar in 1979 at the SEM conference in San Francisco. It was an interesting conference. Caesar at that time was at the top of the heap for people doing optical methods, and he stayed there for a very long time. So he's been a mentor to a lot of us, and I greatly appreciate his willingness to talk to folks that were young as well as the folks that are older. And since I was my first meeting and he was very kind and gracious to me, I really appreciate it. And I hope he has a lot more years to come. So with that as a background, we'll talk a little bit today about work that we've been doing, dealing with trying to find a find a way to automate the process of comparing DIC and FE data at exactly the same points, or as close as we can to the identical points. And we'll go through the process of why we were concerned about this, and it goes back to work that Jeff Helm, who's sitting in the audience today, did at NASA almost 25 years ago. So to start it off, this is the paper that was published recently. It's in a journal that most of you may not know much about, Computer Methods in Engineering and Science. It was the ideal platform for this work. They try to relate one area of engineering to others through the computer methods, and that's what we did. We tried to relate the computational to the experimental, and the journal was ideal for that. So that's where the work is published if you want to look it up. So as we all know, the process is straightforward. You have some DIC measurements. This of course is going to be DIC full field data here. You have an FE simulation that you're going to perform for the same geometry with material property that you're estimating. To compare those, you got to go through a coordinate registration process, and once you've done that, you then compare them as best you can in a full field manner typically. So nothing new there. This is the standard approach that we've been using for years. What first came up when Jeff did this work at NASA, I'm going to spend a little bit of time on this because it's the foundation for why we got into this. This is a wide panel test that we did at NASA, circa 1999, 1998 timeframe. This is the region we took data for. This is a center crack panel. It was, quote, fixed, unquote, at the top and mechanically loaded at the bottom. These are the full field data, and this is the largest load here. And as you go up, the load decreases here. Look at the V displacement, which is vertical. And what you see is the lower grip area, which should be flat, it should be straight across. The displacement should be the same everywhere, even for the lowest loads was not. So something was happening at that point. It got worse as the loads went up, and at the bottom you can see there's a large scale displacement of one side relative to the other, which means it's rotated. It's either slipped out of the grip or something has happened. The reason this became important is because the modeling folks got very upset when they could not match our data. They started asking questions about, look, we modeled this and we're not getting anything like you are. And we're not predicting the buckling. This panel actually buckles locally in here around the crack. There's a compressive field, if those that don't know much about center crack panels, and it tends to cause a buckling phenomenon locally that we can measure, but they had trouble predicting what we were seeing because of this slippage. So after putting in this information to them, we went back and Jeff redid the experiments as best he could, modified the grip, and as a result, we got much better results. As you can see now, we're looking at all the data underneath. And the data, this is the DIC for the horizontal displacement, and there's the FE. And as you can see, as you walk across here, the results are quite good, at least in a full field manner. The fringe patterns here look roughly like the fringe patterns here. The contours are similar. They're the same here. If you look carefully here, there's differences. We don't talk much about it, but there are clear differences nearby. We didn't quantify that in great detail at the time. As time has gone on, it's become more and more important to ask the question, well, what are the differences here and what do they do to? If you're going to do this, a full field approach certainly works, but there's also questions about at individual points in the field, how well are you predicting what's there. So that's the background for this. That's where it all came from. Jeff's work gave us the indication that if we're going to really compare in an honest, straightforward manner, we got to have the right boundary conditions. We got to have the right comparisons of data. So, an improved method, in principle, you have the DIC measurements. You do some sort of coordinate transformation or registration here, which includes boundary conditions and geometry that are then fed to the FE simulation in the appropriate way, and then you can compare after they've been properly registered, directly compare the results. So that's the idea, is you got to connect these in a way that makes sense. But let's talk a little bit about StereoDIC and what is a coordinate system. How do you define coordinate system? I guess it depends on the software. I'm going to talk only about VIC3D and Correlated Solutions software because that's what I'm knowledgeable about. Okay, but the same ideas are going to fall across to others. Okay, the default coordinate system in StereoDIC is typically defined by the calibration grid. There's some point on there that's the origin. There's a coordinate associated with if you have a series of dots in there with the X along one direction, the Y along the other, and the cross product giving you the Z direction. And that's your default coordinate system. Obviously, that's not going to be the same as the coordinate system on the specimen or in the finite element model. So you have to redefine it. And to redefine it, you have to go in some way, either in the software or in post-processing mode, to transform things till they're all in the same coordinate system. And in the end, this type of comparison, if this is a subset from here, you have to know where that data is if you're going to compare it to finite element. Where is it in a same coordinate system, in the same geometry, in same orientation as what you're using in the model? We all know that. The goal is to try to put something together where it's easy and simple to apply in applications. So how do you typically do coordinate registration? There's all sorts of ways to do this. You can talk to folks in all sorts of areas, and you have fiducial marks. You can align axes by exploiting symmetry. You can use a touch probe. Some colleagues of mine at another university were using touch probe for some of their registration processes. And most commonly used are natural features, corners, edges. You need several of them. You can't just pick one. You got to have several, as you all know, so you can get the proper rotation and the proper transformation, in this case translation, so that it's as accurate as possible to match them up. So all of these are feasible and have been done in a variety of areas. So there are three ways that I view that you can do this. You can transform the data to the FE nodal locations. Most modelers want that. They want to go that way. They want to shove over things over there so they can match up. Obviously, I'm an experimentalist. I don't give a crap what they think. Okay? I want to put it in my coordinate system. Okay? You can also transform all into a pre-specified coordinate system. This was done by a colleague of mine, Steve McNeil, way back in the 80s when he was doing work using the Williams expansion solution in our theta coordinate system. He wanted to convert things into a system he defined for his model. There was no finite element model. It was just a standard asymptotic expansion approach. So he did that way back then. But of course, it wasn't that accurate, but he did a good job and it worked out pretty well. And the one that we're going to talk about today is the one where we're going to transfer the FE nodal positions into the measurement locations. Okay? And of course, I've already mentioned these. This transformation can be useful at times if you have a theoretical model or an asymptotic expansion approach that you want to compare to. We're going to be talking about this one. Of course, you can go any one of these you want. I'm just going to talk about one of them. You can switch it as you want to go from one to the other. How am I going to show this to you? Before showing you the flow chart, let's show you what we're going to try to use it to explain the process. We used a 6061 T6 aluminum specimen with double edge notch. This is the stress strain curve that we got. We did this in the lab at USC, South Carolina. And so the data that we got here is not from a handbook. It's actually for this specimen. And this is the average of 3 tests. So it's a pretty reasonable approximation for what's there. The geometry of this, we're loading from 0 to 35.1 kilonewtons. It's roughly 4.8 millimeters thick. So it's a simple specimen, but it has a lot of detail in it that's interesting. The notches the interaction of the notches, and the regions away from the notches that are going to be fairly standard. So all of this you're going to see in the results. So it gives you ask the question, can we get good data here? Can we get good data here? Comparisons have to be good everywhere. Obviously, most people are interested here and here, but we got to find something that works all throughout the region in case there's specific regions you're interested in. Calibration process, we all know how this works. The StereoVision system, this is the data we got for our StereoVision system. I call your attention, these are standard, you can look them up wherever. There's two parts that are important here. First of all, the subset size is the same size as the strain filter. That means there's no, whatever you see for the strain, the average value you get for the strain is the same as the subset size used to generate the data. So that's the first part. This is the magnification, 20 pixels per millimeter. We roughly had more than enough pixels per speckle and more than enough speckles per subset to generate highly accurate data. Here's the accuracy in the data down below. The median and the mean are almost zero. They're down in the approaching nanoscale accuracy. There's no bias in the data. We end up with accuracy in the strain of about 120 microstrain for this data. So the data we get from our filters and everything that we use for this, all around 100 microstrain. So that's the background for it. Here's the model for the specimen. Notice that we're only taking this central region. We also followed what Jeff Helm did. We input the data up here not as stress. We input the actual measured displacements. We realized that we had problems. This region actually did slip a bit. The loads were right, but there was not perfect alignment here, so we simply input the correct displacements here and here from the measurements. They're input along this top surface and along the bottom surface. They're done a specific way. I'm going to take a little bit of time with this. Along this yellow line, we input all three displacements on the top and the bottom. On the green region, we only input the U and V, the in-plane displacements in the X and Y direction. We let Poisson's ratio effects do whatever it wants. So the specimen can contract inward if it wants to, which it did, and we didn't require it to do anything other than what it wanted. Whatever it did was fine with us in the model. So the modeling part of it allowed this to move in freely on the back side, but it did go up in the X and Y direction corresponding to the displacements we measured as if it's on the front surface. So it's a plane stress type approximation. The other thing we had to do for this was a convergence analysis. If we're going to compare this stuff, we got to be sure that the final element model is converged. We got to know that the results we got are as accurate as we can get them. So in this case, we used a whole series of meshes. We did 9 different meshes. I'm just showing you 3. The smallest number and the largest number. This one, 180,000 nodes and 35,000 elements, was the one we used. And it worked well. The errors, the difference in strains between mesh 2 and mesh 3 are very small, down 0.09, 0.01% of the previous strain. So the accuracy is quite good. And so we were satisfied this is going to give us quality data. Okay. So one may ask, well, how do you know that what subset was best? Why did you pick 45 by 45? You can do that with all sorts of different ways to look at the data. What we opted to do was just take a line of data here and choosing different subset sizes. We plotted the strain, the vertical strain along that line for different subset sizes. And what we chose was the subset that gave us the best approximation to the gradients. And that is the gradient meaning this rise and drop off as you move from the center of the specimen up toward the top. Obviously, we chose the one that gave us the best result as far as picking up the high strains that are there. So in that case, this was chosen, and it was 45 by 45 subset, which is why we chose the strain filter the way we did. All of these are important if you're trying to verify something. And that's what we're trying to do, trying to show how this works in application in a way that people can employ without being too worried about how to get there. This is the kind of experimental results we got for this test. I'm only going to show 4 and sometimes only 3. The results are similar for all the cases. This is in this case, the horizontal strain. And this is the XX, the transverse strain. This is the shear strains here. They're not big, but they're clearly visible. And we're going to see more about these later. And of course, the high strains around the notches are visible. This white line is going to be important. We're going to use it in a minute. I'm just putting it there so you can see it. It's going to be a place where we're going to directly compare the results as we move forward. Okay, this is the results from finite element with the von Mises criteria. In this case, we chose it because we assumed that the material was isotropic. Okay, anyway, it looks good. And there's that line again. And it seemed fine. If you look at what Jeff did earlier with the fringe patterns and the contours, you look at this, they look very similar. Things look like they're going to be as accurate as you need. But we took a little more look at this. And what we did was we go in and we took that white line you saw at the bottom notch, and we plotted the strain along that notch. In this case, this is delta x, EXX, the difference between the finite element and the measurements. And we clearly see, as we get closer to the notch, we got a problem. The strain accuracy is almost 6,000 microstrain off. This is using direct point-wise comparison. This is after we've completely registered the patterns to each other, okay? And the process for that, as we noted earlier, requires you to go through a series of transformations to do that, which are completely detailed in the paper. So you can see how we did it. And over here is EYY, the vertical strain. Again, we're 3 to 4,000 microstrain off at some point. Well, at that point, we had to ask the question. We know the convergence, the finite element mesh is converged. We know the data from the DIC is accurate because we saw the noise levels. So the question is, where's this coming from? And we immediately, after going back and looking at where we got the material, we realized we had a problem. The material was hot rolled. And anybody that knows anything about processing of materials knows that's not going to give you isotropy. The differences may be small, but they're going to be there. And I think we're picking them up. So we went back and said, if we have the stress strain curve in the y direction, let's go back and pick up some models that would represent approximate representation for anisotropy and yielding. So that's where we went next. The first one we did, and this is the simplest one. This is the original Hill's quadratic anisotropic yield criteria. For those that know much about this, and I'm sure there are people here that do, this is from 1948. I mean, this is back a ways, and it's still used today. This is the one that's implemented, for example, in ANSYS. They don't have a lot of them in there, but this is one of them. So we were able to use this. The question is, we have in here, in this is a plain stress version, we have 4 parameters. We don't know those parameters. So how do we get those? How do we estimate those so we can go forward? Well, we decided to try a method that is well known in the community, and that is to take the data that we have and see if we can use it if we have enough variations in the stress field within the specimen, and try to estimate the parameters with the data we already have. It turns out it works pretty well here. So what we did was we took 36 of the 40 sets of data in here. We don't use the 4 that we're comparing to. You saw the 4 loads. We don't use that data. But we use the data from the other 36 loads that we had. We plugged those in we developed an optimization procedure with the finite element. We iterated on the parameters, and there are 4 of them here, until we got the best possible comparison. Once we've done that, we then found that these are the 4 coefficients, and these are the relative comparison of the yield stresses in the 4 directions. And this is the yield and shear. So it's not much different, 15% difference. In the transverse direction, it's 20%. In the vertical direction, it's almost dead on. So of course that would make sense because that's the yield stress we had. And in the through thickness direction, it was in the R33 direction, which corresponds to, I'm not sure what I think of as the H component, that's 0.95. So we had them. We could estimate them, and the differences are not big in yield. 15, 20% difference is the worst we had. This is a comparison of our parameters to parameters in the literature for a similar material. And you can see that the differences are small, but they're there. They're not perfect. So we need more, you got to do more studies on this, more experiments, more analysis to improve the quality of these 4 parameters if you're going to use the Hill criterion. But it works well just with the data we have. So the question is, how good is this if we do this? This is what it looks like, the strain predictions with Hill's quadratic anisotropy yield criterion for those 4 loads that were not used. When you compare those, we're going to compare those now, of course, to the DIC data. Here it is at 1 point. This is the first one, right down at the lower notch. This is with the von Mises criterion, and this is with Hill's criterion. The difference here is 300 microstrain. That is the largest difference we had anywhere in the field. For all the strain components throughout the field, the largest difference was about 320 microstrain. So it matched up very well in a full field manner with these parameters. Here's the full field version of it. These are the differences now, okay? You can see the differences are small everywhere. This is 6,000 microstrain. You see no reds anywhere. You're down in the greens and blues, which is down in the center. And near the notches, 400 microstrain, or 200 to 400 microstrain, around 300 is what we're seeing the differences. And that's throughout the whole field. So the results for all the strains in the entire field were good with those parameters. Okay, now, initially this was where we were going to stop and talk more about the details of this. But at that point, we were asked the question, could we not, if we have the material parameters, can't we just use the strain field? We don't need finite element and just get the stress field. And the answer, of course, is yes. You just have to have the appropriate Hill's yield criterion, or whichever one you want to use, programmed separately as a module, if you will. You can think of it that way. So we decided to do that. So the student, Troy, implemented 9 or 10 models, including kinematic hardening. And as a result, one of them we did was the Hill's anisotropy yield criterion. And eventually, Correlated Solutions, Vic3D, decided they just put this stuff in themselves because they were curious about how it would work. So it's now embedded in the code, but more importantly to me, how well does it work? What does it look like if you compare the stress fields? The strain fields look fine. What about the stress fields? This is the type of interface you have if you want to do it in the code that they have today to utilize it. And again, this is more of it. You just follow through the layers to get to the final prediction, and this is all stored within Vic3D for your use. This is a comparison without the video of the Vic3D computed. This is the one that uses only the displacement and strain data from the experiment, and this is only the ANSYS model. And they both have the same, in this case, the Hill's quadratic anisotropy yield criterion. And to see what it looks like in video, I'll show this. We have 3 of these for you to see. I think it's important that you see how it evolves. You can see that the interesting part was we do see the connections of the strength of the field across the ligament as we expected for the signal YY. So the transfer of load into the material can now be determined if you just go through this process, and you don't need the model to do that. You simply can use the data and existing software. Okay, that's what that looks like. This is what it looks like for the transverse stress. This one actually was not quite, because the stresses are fairly low, 150, but if you look carefully, this field here is not as well developed if you use the data. At least it doesn't look like. Later on, it becomes much more similar. But again, the strain differences are small everywhere. So the noise in the data is clearly visible in the stress field that you're calculating. As it gets further in, these become more clearly similar throughout. And the difference is, of course, you're multiplying by a large modulus. This is my favorite of all of them, the shear stress field. When I first saw this, it's almost like a painting when you see it. There's so many loads to this field. It's kind of hard to imagine it. I don't think I would have imagined this until I saw the video. these kinds of connections across here are hard to visualize for me. But again, you can see the noise is still there. It's just that as you get larger and larger, the noise becomes less and less of the signal as you go. And the last thing is you can also do point extractions on these. You can come in and out, particularly if you want to know what's going on in that notch, you can pull that data out, and there it is right there. Again, the differences are here, and this is the comparison of the fine element and the measurements for the estimated measurement value from the only measurements in the model. And the differences here are quite small. Okay, so that's it for that. Let me summarize what we've done. We've gone through a process of developing the software, all done in Python originally, as you guys would expect, with Python codes, to convert everything into a common coordinate system, both translation and rotation. Once you've done that, the registration process is done, you can now go in and at the same spatial locations, compare one to the other. Nodal data directly to experimental data. And basically the experimental data, in this case, the nodal data is interpolated to the experimental data locations as part of that process. You compare them at all the locations. We use PySoft extensions to do that. We demonstrated it for this double edge knot specimen. The simulations were performed using endpoint displacements. Again, much like Jeff Helm did, we had to do that. We couldn't get good results unless we did that. Point comparisons were found to be good. It turned out that we had to go to the point by point showed us we had a problem with the material properties. And that allows us to go back and find a way to estimate those using the existing data. And from that, we then were able to get good results when compared to full field stresses. References are here. And I'll close with that. Thank you.